Thank you for joining me as I go through the source code and some interesting technical things about the Apache Lucene. So Apache Lucene is probably powering the search of the internet in many ways that we may not actually see, but it does power powerful tools that are used by software around the world. The most commonly known one, I think, is Elasticsearch, which uses Apache Lucene. Solr also uses Apache Lucene. You may be using one of those services directly, or you may be just browsing a website and using search where it's being powered by Lucene. But if you go down to the bare bones and you want to use Lucene directly, this is how your code would look like in Java. So let's just focus on this part where Lucene has a class called analyzer, and then the analyzer will work on a configuration. So you create an analyzer, create a directory, then create a configuration with the analyzer. In this case, we are just using an in-memory directory, which is basically faster to prototype things. And then create an index writer. So all of this is essentially creating a whole bunch of objects so you can write data into Lucene. And document is the entry point. So a document is the minimum unit that you write into Lucene. And each document is composed with object called fields, and each field has a field name and a value, and then you bunch of options essentially. In this case, we are trying to store this. So we are adding the field to the document and then adding the document to the writer. That's how Lucene gets a document indexed. So in this case, we index a document which just has a field called field name. The field name has a value of the text to be indexed. I'm going to skip a few lines here, but in this case, if you just focus on here, so now we are going to the same index and trying to search everything that matches the query, like human written query text, and it just finds the document back. That's what it is asserting. So you basically give it a human readable document and then give it some criteria for tokenization, and it will give you full text search capabilities. What's fascinating is if you go to the Lucene project on GitHub, you will see that this project has been around from 2002 on GitHub, Git history at least, and then it has never really slowed down. Like even last week, if you see the pulse, even last week it has seen close to couple thousand lines of code changed. And if you look at the last month, this project is still very, very active. 41 people contributed with thousands of changes in the last month. So even though it's a project that is almost 18 years old as per Git history, it's still actually very vibrant and live. So now let's go ahead and take a look at the main model that we saw here, which is the document. I'm just going to focus on documents. A very large project, can't really go into too much details about things. But today I'm just going to focus on how the object-oriented structure is used within Lucene index. So Lucene GitHub project is a combo of both Lucene and Solr. Again, Solr is a web interface on top of Lucene. So Lucene is sort of the core engine that does the indexing and analyzing. So within Lucene, I'm again going deep into the core, and inside the core you will see a whole bunch of things. I'm just going to use a shortcut and go to the document.java, which is sort of the minimum unit that you can put into the index. So it's very straightforward to follow. The document class is just an iterable of indexable field, which is quite easy to understand. A document is composed of indexable fields. It's not a dictionary, and it's an iterable because you can have multiple values for each field, things like arrays. And because it's an iterable, it just implements a whole bunch of iterable methods. Like you can add a new indexed field, you can remove a field, things like that. And the fields are of a type. Let's look at the field. So indexable field itself is just an interface which defines, so each field has a name and a type and essentially value. The values are either bytes or a string or numbers, things like that. And of course, to produce indexable field, you can use a token streamer. So now this is an indexable field, which is an interface. And I mean, as you would see with many Java classes, it's very common to declare an interface for basic interface. And then there's an abstract class called field. Oh, sorry, I should be looking for field.java. So field is the main implementation of indexable field, which you can imagine just implemented methods. So a bunch of constructors and different ways to construct it, but eventually creates a field. And then it implements those, type methods of it can give you a string. If it's a string, it can give you a character sequence, like give you a reader, give you a binary or number values out of it. So nothing too crazy about the field implementation of the indexable field. If you want to look at a specific implementation of a field, let's look at string field, which is of type string, of course. Here you see that the field type, they are defining two constants, one for stored and one for not stored, essentially. And they have some static blocks, which is this code gets executed every time this file is loaded in memory. Essentially, this class is loaded in memory. So there's one variant which is not stored, and there is another variant which is stored. And the big difference is one is not set for storing. And then you see two constructors. So of course, this one just takes a string value, and this one takes bytes as a value, even though it's a string field. And that's okay, because you could use encoding. Of course, if you look at these two constructors, this is what a pattern I saw across all the fields, is they are very similar. The only difference is in the type of this second parameter, which I think using generics, they could have just used a single definition of it instead of two different definitions. But this code has preferred this approach. Instead of using generics, they just override the constructors with specific types. So similar to string field, if you go to the document sort of namespace, there are a lot of other different field types. Let me see another one maybe. So let's look at text field, which is a little bit different, but also again, you see there's type not stored and then type stored. And this pattern again repeats across the different types of fields. You see that these methods are not very different, and probably using generics could have simplified a little bit of this. But overall, the document class, now if you look at sort of what constitutes a document has many fields. Each field has a field type. Each field is either stored or not. So if you look at the stored field, so stored field is a field which basically just sets the stored variable, stored attribute to true. And again, very similar looking constructors, quite a few of those. There's not much logic otherwise other than that. And Lucene out of the box supports many different types of fields. We looked at string and text, but there is also a field like a point, which is like an XY point, as you can imagine. This is good for finding similarity and distance math using Lucene. And if you look at the document test, then we can find out how Lucene is testing. It's very straightforward testing, to be honest. This is just creating a document and adding different types of fields, because document is an iterator, and then just verifying the iterator works. One pattern I see that, unlike many other libraries, Lucene doesn't worry about adding quite a few different test cases in a single test, which is fine with me. It's just a pattern that I see some projects will say you should not have too many assertions in a single test. But in this case, these tests are very straightforward. So overall, I found this code to be amazingly simple to traverse. Once you know the basics of how to use Lucene, you can almost find a place where to get to understand how Lucene internal works very easily. The object orientation is surprisingly simple. It matches your mental model. There is like naming of things are really good for the most part. One thing I didn't like is, for example, they call it string filled when it's a string filled, but for some other types they don't add the field name. For example, binary point is also a field, but it doesn't have the name binary point field. I think like having that little bit of discrepancy in the names makes it a little bit difficult if you're new to this code to know whether or not binary point is a field. But I think it's not a big deal because you actually see the namespace, it's in the document, and you can almost guess that anything in the document is a field by that, like, and you can use that information. One thing that I was really impressed with is like they have a benchmark test suite that is publishing results for the last 2 years. And I've never seen anything like that in any other project. So this is last 2 years of benchmarking of indexing performance. And every thing that you see in the tags, these are significant changes that happened in the code over time. So for example, between these, I think somewhere in November, December of 2018, and this somewhere in April, May of 2019, we see that performance went down significantly, but there was no significant feature changes as per their own coding. But at this point, you see a sharp spike in performance here, and there was a little change. You can see that they switched to OpenJDK, and that gave them a little bit of performance boost. But in terms of raw numbers, they are taking, documents that are 1 kilobytes of size from Wikipedia, and they are indexing at the rate of somewhat around 600 gigabytes per hour. But when they use a larger document, then they are indexing a little bit at a higher throughput of close to 800 gigabytes per hour. And it's quite nice to see like how they have been able to preserve this data from years. So you could see how performance suffers not just from big features, but sometimes from small changes in the code. Another thing I saw was very interesting was the Boolean queries. This is like AND queries when you see how performance took a significant improvement at that point. And if you see what happened, the big change at that point was stop counting total hits by default. So changing a default behavior, they have gone from 10 queries a second to like 24 queries a second. And another one is here, proximity queries. You see that the performance sort of had like step function improvement. So at this point, they have changed something where they said, okay, we are going to load frequency blocks lazily. So something that is not loaded right ahead until it's needed. And that has improved performance from 8 queries a second to more like 22 queries a second. So it's really nice to see these historical graphs. That gives you perspectives if you are new to this project. That gives you quick feedback if some unrelated changes may have degraded performance. So I hope you have enjoyed this episode of me showing some code inside Apache Lucene and these interesting performance graphs that they produce. Thank you so much.